Hi everyone, welcome back. The learning goal for this video is to be able to use specific heat to calculate heat energy that is lost or gained. And here we see a beautiful picture of the beach, and we will discuss in this video how the high specific heat of water keeps the temperature of the ocean more moderate in summer and winter. It doesn't fluctuate so much due to water's high specific heat. So what is specific heat? Well, it's different for different substances and is defined as the amount of heat, energy, remember that's Q, that raises the temperature of exactly 1 gram of that substance by exactly 1 degree Celsius. So every substance has a different specific heat, and I would provide you those values in a table or within the context of the problem on an assessment. Specific heat is abbreviated as capital S, capital H, and it has different units. It can either be joules per gram degree Celsius or calories per gram degree Celsius. And this formula here is the formula for specific heat, which is Q. Remember, heat is Q, so let's write that down. So that is Q divided by grams, which is mass, times delta T. And I want to remind ourselves that anytime you see delta, that means change, and that means final minus initial. So delta T is the change between the final temperature and the initial temperature. So delta T in this case is TF for final minus TI for initial temperature. And once again, every substance has a different specific heat capacity. And for water, it is 1 calorie per gram degree Celsius, or 4.184 joules per gram degree Celsius. So what that means is that in order to heat up 1 gram of liquid water by 1 degree Celsius, I need to provide that water 4.184 joules of energy. And I like to relate a lot of what we learn in chemistry to cooking. So for example, if we're comparing the specific heat of copper metal. Now, copper metal pans are state of the art in cooking, and that's because they have a low specific heat. So I'm going to be primarily looking at joules, but remember you have also specific heat in calories as well. But if we look, for example, at copper versus liquid water, the state of matter does matter. But in this case, I'm focusing on liquid water. There's a big difference between copper and water. So for example, copper. This means it only takes 0.385 joules to heat up 1 gram of water by 1 degree Celsius. So that is why copper is a great material for cooking, because that metal heats up really quickly. So when I put my copper pot on the gas stove and I give it some heat energy with the flame, then that pan is going to heat up real fast because it has a low specific heat. Versus if my pot was made of aluminum, right? It would take more energy to heat up the same amount of aluminum. And so once again, that's why copper pots are valuable for cooking and also more expensive since they do perform better. Now looking at water, this has the highest specific heat in this table here, and that's a good thing, right? You can imagine even cooking, if you're boiling a pot of water to make pasta, it takes a long time to boil the water, right? And that's because water has a high specific heat. Another thing I like to give an example for is that our bodies are composed mostly of water. And that's a good thing because some of us live in different parts of the world where it can get, in triple digits real fast every day, like 120 degrees, right? It can get super, super hot. And if we were to walk outside, we don't want our body temperature to raise too drastically because that could be lethal, right? And so our bodies, because they're made of water, can moderate the temperature so that, for example, we don't spike a fever walking out on a very hot day somewhere. And also so that we don't get too cold as well. If we're like in Antarctica, right? So it's one of those things that our bodies are able to moderate our physiological temperatures due to the fact that we're mostly made of water, which has a high specific heat. If our bodies were made of copper, that would be a problem. If, for example, I walk out on a hot summer day in Texas, right, and it's over 100 degrees outside, then if my body was made of copper, I would heat up too quickly, right? And that could be lethal. So wanted you to pause this video, try to do the study check on your own first, and then check back with me when you're done. All right. When ocean water cools, the surrounding air, does it cool as well? Does it warm, or does this stay the same? Well, this was a tricky question. We haven't talked too much about law of conservation of energy. Which means energy cannot be created nor destroyed. And so another way we can represent this law is energy of the system, which I will abbreviate SYS, plus energy of the surroundings, which I'll abbreviate as SURR, is equal to 0. So the energy of the system plus the energy of the surroundings is equal to 0, which means it doesn't change. Energy cannot be created nor destroyed. Okay. So in this case here, we're going to treat the ocean as the system and then the surrounding air as the surroundings. So I'm going to say Q ocean plus Q air, which is the surrounding, is equal to 0. I'm going to move Q ocean to the other side so we can see the relationship between Q ocean and Q air. So I'm going to subtract both sides by Q ocean. And so that will give me Q air is equal to negative Q ocean. So what that means is that the heat energy lost by the ocean is equal to the heat energy gained by the air. So when we discuss energy and you see positive and negative, negative means that energy is released. And if heat energy is released, a lot of times that means you're getting colder. So once again, the ocean's getting cooler, so it's releasing heat energy. A positive means that the energy is absorbed. So due to the law of conservation of energy, if the ocean is getting colder, that heat energy that was in the ocean is being released and it has to go somewhere. It can't just be destroyed, right? It's just going to be transferred, and it's going to be transferred to the surrounding air. So when ocean water cools, the surrounding air warms. Now, sand in the desert is hot in the day and cool at night, so it changes temperature drastically. Does sand have a high specific heat or a low specific heat? Good. Hopefully you said low specific heat. We saw that with the copper metal having such a low specific heat that it can heat up really quickly and also cool down pretty quickly. So anything that fluctuates in temperature, any material or substance that can do that drastically will have a low specific heat. Whereas materials or substances that have high specific heats tend to moderate their temperatures, like water. All right, let's do some calculations with specific heat. When we know the specific heat of a substance, we can calculate the heat lost, remember that's heat energy Q, lost or gained, by measuring its mass and temperature change, TF minus TI. And we will use the heat equation to help us. So heat, remember, is Q, is equal to mass times the change in temperature times specific heat. This is the specific heat formula we saw earlier, rearranged to solve for Q. So if we go back and look at the specific heat formula, that is this formula rearranged and solved for Q. So that will be a good core chemistry skill to master, is using this heat energy equation. So how do we approach these types of problems? Well, as always, we state the given and needed quantities from the word problem. We then calculate the temperature change. Delta T is equal to TF minus T initial. We write the heat equation and any necessary conversion factors. If the units aren't in the appropriate units they should be in. And then finally, we substitute in the given values and calculate the heat energy, making sure our units cancel. So go ahead and try to do this study check on your own, pause the video, and then check your work with me when you're done. What is the specific heat if 24.8 grams of a metal absorbs 275 joules of energy and the temperature rises from 20.2 degrees Celsius to 24.5 degrees Celsius? So let's write our given. So we have mass of the metal is equal to 24.8 grams. We also, it says it absorbs 275 joules. So when I see units of joules or calories, I know we're talking about heat energy. So 275 joules. And the temperature rises, and it's really important to read this carefully so you can determine what is TF and what is TI. It says from 20.2, so that implies this is the initial temperature, to 24.5, that implies that is the final temperature. So we have TI initial is 20.2 degrees Celsius. TF, which is final temperature, is 24.5 degrees Celsius. And we need specific heat because this is an unknown metal. So we don't know the identity of the metal, so we can't look up the specific heat. We're using these values to help us figure out the specific heat of the metal. So whenever you're working these types of problems, either specific heat or heat energy, you have to determine which formula to use. Because we're looking for specific heat, let's go back. We're not going to use this formula here because it solves for Q, and we already have Q. We're going to use this formula here. Specific heat is equal to Q, heat energy, over grams in mass times delta T. I'm going to write that on our problem here. So specific heat is equal to Q over mass times delta T. So immediately I see delta T needs to be calculated. So I'm going to calculate that here. So delta T is equal to TF minus T initial. So TF is 24.5 degrees Celsius minus 20.2 degrees Celsius. So 24.5 minus 20.2 is equal to 4.3 degrees Celsius is the change in temperature. And then I can plug into our formula. Specific heat is equal to 275 joules divided by mass, 24.8 grams, times 4.3 degrees Celsius. And so when you're plugging this into your calculator, I like to put parentheses since there is multiplication in the denominator of this formula. So I'm going to plug in 275 divided and then in parentheses 24.8 times 4.3 into the parentheses, press enter, and I get the specific heat is equal to 2.57 joules per gram degrees Celsius. And now this is all multiplication and division. So remember, report the final answer to the least number of significant figures. So in case that is 2 significant figures, so the final answer would be 2.6 joules per gram degrees Celsius. No units cancel out. Those are the units for specific heat. And so I'm going to go ahead and highlight our final answer. There we go. Now, if you had a practice problem or a word problem that asked you to solve for a heat energy Q, then remember you would have to use the formula Q is equal to mass times delta T times specific heat. And you would need to know the identity of the substance so you could look up the specific heat. It's going to be provided either in a table or within the context of the problem. All right, thank you for watching and email me with any questions.